Hey everyone, good morning, good afternoon, or good evening, wherever you are located, and welcome along to the AMETEK Solid-State Controls monthly webinar for August 2024. Thank you for joining us. The topic this month is charger troubleshooting and basic charger information. So what I will do is, as always, ask everybody if you can hear me, because there is no point in me speaking to myself. So if you could comment in the chat bar if you can hear me or not, that would be really appreciated while we wait for everybody to come into the room. And while we wait, I just want to say, we really appreciate you taking the time out of your day to come and visit us for these webinars. We hope they give you good information, and we know your time is precious, so we really do appreciate it. Thank you, everybody, saying that you can hear me. So that means we can move on. So let's go through the admin side of things. So first of all, hopefully you know me by now, but my name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solid-State Controls, based in the Stafford, Texas office. We're just on the southwest side of Houston. I have over 23 years in the industrial UPS industry now. And I've worked with all the major UPS manufacturers. I've worked all over the world, and I've worked with most of the major brands, and I've been with AMETEK Solid-State Controls for 7 years now. Regarding the platform we use Webinar Jam, and there's going to be pretty much a lag of 30 seconds between you hearing my voice and from when I spoke. So there's a delay. Basically, Webinar Jam has to take this broadcast, and it's got to change it into iOS, Android, and into Windows-based webinars. So there's some processing time that happens, and that is between 15 and 30 seconds. So when I'm speaking, you're not going to hear me for about 15 to 30 seconds after I say it. So therefore, if you have a question, I'm not going to see it until 15 to 30 seconds after I have said something that may have triggered your question. I'm rambling, but my point is that what I tend to do with all the questions, first of all, don't put them in the chat. If you look on your chat bar, we have a chat tab at the top, and then we have a Q&A only. If you have questions, go to the Q&A only tab, type your question in there, and then at the end of the webinar, then I'll go through all of the questions and answer them one by one. That way I'm not stopping and starting and trying to figure out why you asked that question when it was 30 seconds after I spoke. Hopefully that makes sense. Also, Webinar Jam has a panic button, and I'm not going to tempt fate. So all I'm going to say on it is, if something goes wrong, if the room freezes, if somebody says you can't hear me or that it's frozen on your side, then I can press the panic button. What it does is it starts a new room, invites everybody back into that new room, and we start from where we left off as if nothing had happened. So that is available. The other very common question is, will the webinar be recorded? And yes, the webinar will be recorded. Webinar Jam records the video for us. And if you signed up for the link, then you will receive a link to the recording. But the problem with the Webinar Jam link is it treats it as a new webinar. So you press play, and basically you've got to watch it from start to finish. You can't rewind, fast forward, and do stuff like that. So what our fantastic team in London has posted it in the chat bar already. London basically takes that Webinar Jam video and converts it to an MP4 and then uploads it onto the AMETEK Solid-State Controls YouTube channel, where all of our previous webinars live. So our whole library is on our YouTube channel, and it takes about up to 24 hours for them to convert that video and get it onto our YouTube channel. But if you follow that link that London has put in the chat bar, that takes you to the YouTube channel, and you can peruse at your leisure. And the last thing is the webinar should last around an hour, but as you probably figured out already, I do talk a lot. So sometimes it can go a little bit longer than I expected. So we'll see how this one goes today. So first of all, we're going to go through what we're going to discuss. So we're going to understand what a charger rectifier is, just a very quick overview. And for more in-depth details, you can visit the YouTube channel. I've put the link in there, and also London's put the link in the chat bar. And go to the webinar that's called Understanding DC Chargers and Rectifiers. Okay, and that gives you a much deeper dive into what a charger rectifier does, how it does it, and all of the semiconductors and controls that are involved in doing that. Okay, for this webinar, we're just going to do a quick overview. Then we're going to go over how to check input problems, how to check if there's any transformer issues, how to check if there's any semiconductor issues, the SCRs, how to check basic control board issues, and then how to check if there's any filter circuit issues. Now, remember, this is not going to be an in-depth. You are not going to become a troubleshooting expert by the end of this webinar. It's just going to give you a few pointers, and it can be referenced to most SCR-based chargers, not just AMETEK solid-state controls, but mostly if it is an analog system. It's not a processor-controlled control board, but it's still relevant, and you'll see that as we go on. Okay. So, first of all, what is a rectifier? What does it do? So basically, it converts AC, where the waveform periodically reverses direction, to DC, which flows in only one direction. And there are two main types of rectification that we deal with today, and that is half controlled and fully controlled. Okay, and we may go into that in just a moment. But rectification is used in chargers to convert AC into DC to basically charge batteries and supply critical DC loads. That load could be an inverter, or that load could be a lube oil pump or switchgear systems, whatever. Okay. And the components of a charger system, the basic 6 components are an input breaker, a transformer, fuses or protection, thyristor SCR diode bridge, a control circuit, and a filter circuit. They are the major 6 components of a charger system. Okay, and here is a basic charger drawing. And this is from an AMETEK SCR battery charger. And I can't remember if we do break it down on the next page. So we'll start off with the AC input breaker. So you can see the AMETEK solid-state control drawings are usually drawn with reference left to right. So power flows in here and then exits here. So that's the way that we do our drawings. I know that in some European drawings they do up and down, but ours are left to right normally. Okay, there are caveats, but normally they're left to right. So you can see here we have AC input breaker CB1 here. Okay, so that is a way that you can apply power to the system or disconnect power to the system. And also it has some current protection in there as well. Okay. So there's not much that can go wrong with a circuit breaker. Yes, after a long period of time, the mechanics can seize up, or coils and trip breakers can burn out and stuff like that. But in the grand scheme of things, an AC input breaker, not much can go wrong. I'm trying to read what it says here. For AMETEK, we do have a circuit that trips the breaker. The reason why I'm struggling is because the whiteboard on this system actually covers up my writings. Let me turn this off. Okay. So basically what it's saying here is for AMETEK systems, applying power, closing this AC input breaker basically starts the charger. There is no charger on button. You don't have to go into any software or do anything. Closing the AC input breaker starts the charger automatically without any interaction from you after that. So when you close the AC input breaker, the charger will start up, the output will ramp up to its defined voltage, and everything should be okay. So the only way that really you can check an AC input breaker is by checking voltages both sides of the breakers. And that's quite an important thing to do. So you would have to go A to B phase, and then B to C phase, and then C to A phase. And most of our charges are going to be 480 volts in. And then you can check A to B phase, B to C phase, and then C to A phase with a fluke meter, and make sure that you have 480 volt phase to phase on the other side of the breaker. Okay. And the other thing that you can do is you can go A phase to A phase, B phase to B phase, and C phase to C phase. If the breaker is open, then you should get the full 480 volts across that breaker. And if the breaker is closed, you should get pretty much close to 0 volts across that breaker. If the breaker's closed and you get maybe 5 to 10 volts, then the contact resistance of that breaker is higher than it should be, and you'll probably need to replace that breaker. Okay. Now, also, some systems, in fact, most systems that we have the option to trip the input breaker if necessary. Okay. So on our system, you can see here, I know it's difficult to see because it's small, but it says, oh, let me just do this. It says CB1 shunt trip coil here. And I'm not going to complicate things too much, but basically here is the input transformer for the system. And on the input transformer, we have auxiliary windings, which is just separate windings on the secondary to create voltages that we require. So this secondary transformer here gives us a voltage that powers this fan, but it also supplies this shunt trip circuit here if RLY1 closes. Okay, and RLY1 is powered over here by the control board. And what the control board is doing is if basically it's monitoring the DC of the system at one of these terminals here, and if it drops below 105 volts DC, okay, that is the standard industrial low voltage cutoff for a 60 cell lead acid battery. Okay, and then what it will do is it shunt trips, it trips this breaker. Actually, tell a lie, on this system here, my apologies, that would trip the battery breaker. For tripping the input breaker, if this is actually monitoring for a high voltage situation, so it's actually maybe 145 volts DC, and if we go above 145 volts DC, then what the system is saying is, okay, we've gone out of control. There's something wrong with the control board. Something has happened, and that then it will trigger this relay. This relay will then close this contact, and it will trip this breaker here to prevent power going through and to prevent us overcharging the battery. So my apologies for the confusion. the shunt trip circuit we'll discuss later on, probably, for the 105 volts. This circuit here is for high voltage. It's the high voltage shutdown circuit. So if it goes above 145 volts, this relay here energizes. This contact here will close. The coil for this breaker energizes, and it shunt trips that breaker. Not a good start by me. I do apologize. Okay, so that is the AC input breaker. So that's basically the all the tests that you can do for an AC input breaker. So, and actually, if I go back, if your AC input breaker is tripping, okay, then there's really only two things that can be wrong. It could be something wrong with the transformer, because remember, any protection device only protects, only trips because of upstream situations. So if this breaker trips, it is possible that you have a shorted transformer. Very rare. Transformers are very robust and don't tend to fail very much. Or you could have a faulty relay down here, or the system is above 145 volts. But if you measured the DC voltage on the output and you're at 135 volts, which is what should be expected, and this breaker is still tripping and you know the transformer is good, then what you can do is you can pull this relay, which will prevent this contact here closing, and see if the system goes back to normal. If the system goes back to normal and it allows you to close this breaker, then it's probably this relay here that's bad. It's either got a sticky contact or something like that, and you just need to replace that relay. Okay. The next thing we'll discuss is the transformer. Now, the transformer can be drawn in different ways on our drawings, just between different systems, but it's always going to be a delta Y transformer. We use a delta input. We don't need a neutral ran to our systems. And obviously, this is what a normal three-phase transformer looks like. And the important thing is this: there is isolation. These wires here on the primary, okay, they are not connected to these secondary windings whatsoever. Okay, the way that the power is transferred from the input to the output is through mutual inductance. Okay, it's through the magnetism of the coil. Okay, so there is no physical connections between these wires here and these wires here. This is an isolation transformer. Okay, now obviously you get step-up transformers, step-down transformers. For ours, we usually have 480 volts in, and for a 60-cell lead-acid system, we're going to have about 135 volts phase-to-phase on the secondary, roughly. Okay. And as I mentioned, it is a delta Y. So you can see this is the delta connection, and this is the Y connection. Okay. Now, we don't use the neutral for the rectifier bridge. Okay. The neutral is only used for the control board. Okay. So, and you can see the neutral is on the secondary. We do not run a neutral into our transformer ever. We just do not use it. We just need three phases, A, B, and C phase. And then obviously you're going to run a ground cable as well to ground. We do not have a neutral connector on the input to our charger rectifier systems. So this is a primary and this is a secondary, and it's actually drawn quite well because you can see absolutely there is no connection between these two primary and secondaries, none whatsoever. There is a gap, and that is very important, and I think we get to that a little bit later. Okay. We do use auxiliary windings for things like fans and power supplies. So you know, this is the main winding, and then this is an auxiliary winding that is going up to our control board. And then we've also got it going down to noise suppression board. And on this one here, there isn't any fans that I can see. But we do actually use an auxiliary winding here for a float equalized timer circuit as well. Oh no, and there is a fan there as well. So we have various auxiliary windings on our transformers doing different things, okay? And the most important thing that you can do here, if you think you have a transformer issue, is just check the voltages. So once again, from A phase to B phase, B phase to C phase, and then C phase to A phase, you should be reading 480 volts. Do not go to ground, okay? It's one of the biggest things that people get confused on. You should, when you're doing basic troubleshooting, you should never be going with reference to ground. You should always be very cognizant of where you're putting your meter leads. So when we're measuring here, we're measuring A to B phase, B to C phase, and C to A phase, and you'll get 480 volts. I have no idea what you're going to get if you go to ground from 480. Yes, somewhere back at the MCC, your neutral should be tied to ground, and therefore you're probably going to get 277, but I don't know that, and I don't care. What I do care is that you have 480 volts phase to phase on the primary. And then on the secondary, we're looking for around about 135 volts, okay? Phase to phase, once again. Do not go phase to ground. Do not even go phase to neutral. I want to know phase to phase what your voltages are. So it's 480 volts phase to phase on the primary and about 130 volts for a 60 cell battery on the secondary. Okay. If the AC breaker is tripping, be methodical. You know, what we need to do is lift the cables at the main power side of a transformer. So if we've ruled out that relay that I mentioned on the previous page, and we actually do think we have a problem with a transformer, the first thing I would recommend that you do is you lift this cable here, and this cable here, tape them up, okay? And then switch on the breaker, because that takes out the whole rest of this circuit here, okay? So if you lift these cables and then close this breaker, if it allows you to close, you know that there is somewhere in here that is causing the issue. If the breaker still trips, okay, then we now have isolated it back to somewhere within this portion here. Now, it could be the auxiliary windings, it could be the secondary windings, or it could be the primary windings. So obviously, the next thing I would ask you to do is lift the primary windings at these 3 points here, tape them up, and then close the breaker again. If the breaker closes, then you know there is something wrong with the secondary of the transformer. And then it's difficult. Then you've got to try and individually lift all the auxiliary winding cables to see if you have a short there. And what you can do is, if you still have this disconnected and this disconnected, then what you can do is you can do a mega between these windings down to ground to see if there is a ground fault on your transformer. Okay. I hope that makes sense. Now, remember, when you're testing resistance, windings are seen as short. So basically, if you thought you had a problem and you measured between here and here, you're going to go through 2 windings if you're measuring resistance. And it's going to be really about 0.5 ohms. So you're not getting a good amount of information there. You have to methodically look at what you're doing. And what I suggested, by disconnecting these cables and then doing a mega, basically you would go between this point here down to ground with a mega, this point here down to ground with a mega, and then this point here down to ground with a mega. Okay. In truth, they're all going to be the same because they all have connected windings, but at least you will find out if there is a ground fault on the secondary of the transformer. So that's really all you can do with a transformer. And do bear in mind that it is extremely unusual that you will have a transformer problem. It's not out with the realms of possibilities, but extremely rare that you will see a problem with a transformer. So the next thing we're going to look at is SCRs, silicon controlled rectifiers. They're also called thyristors. Okay, it's a semiconductor switch that has no moving parts whatsoever. Okay, it is turned on by sending a signal to the gate of the device, and it's important to understand that you cannot manually turn the SCR off by removing the gate signal, and I'll explain that in a little bit. It will only turn off when there is close to no current flowing through it, and basically that's a zero crossing point of a sine wave, when there is no potential across the anode and cathode. And the symptom of a bad SCR includes a low output voltage, no output voltage, or if there is a shorted SCR, it will be a blown input fuse. Okay, and I'll explain these. So here are the SCRs. So in most of our systems, especially modern systems, there are going to be 6 SCRs. Okay, now in truth, if you look inside your charger, you will actually only see 3 packs. So there's one pack there, there's another pack there, and there's another pack there. But there are 2 SCRs in each pack, making up 6 SCRs. Okay. Now, if an input fuse blows, this confuses a lot of people. So if one of these fuses blow, some people say, oh, well, maybe it's something to do with the transformer. What you've got to get into your head when you're troubleshooting is the fuse is there. It will only blow when there is current flowing into this side. You know, the current flowing through this side is not going to blow the fuse. So my point is, the fuse will only blow when something after the fuse has a problem. So something upstream from the, well, downstream from the fuse, to be honest. So if this fuse blows, we know that it's something over this side, and you can rule out all this stuff is okay. If that fuse blows, it's something in this section here that has failed. So that's the first thing you need to know about fuses. The other thing with SCRs that you've got to realize is if you're going to do some checks and you isolate the charger with power off, the SCR should be open. And I'm going to get to this in just a moment on another slide, how an easy test for SCRs to tell if they're good or not. There is an easy SCR check, but you've got to remember that there is this transformer here, and these transformer windings give you a path back. But I'll explain an easy way to check the SCRs. Okay. And here it is here. So let's say one of these fuses has blown, and we suspect that an SCR has failed. And here is our 6 SCRs here. 1, 2, 3, 4, 5, 6. Okay. Now what we're going to do is we're going to isolate the charger. We're going to turn off the AC input. We're going to open the battery input breaker. So we've got no AC coming in and we've got no DC coming back. So then what we're going to do is we're going to get our fluke or whatever multimeter you use, and we're going to attach the red. It doesn't matter if it's red or black, but you attach one of the leads to the positive bus bar, which on our system is labeled 338 on this drawing here. So you would go into the rectifier bridge and you would find Y338 and you would attach a fluke alligator lead and clamp it on there. Okay. And then you would take your other lead and you would attach it to this cable here. You can use an alligator clip or you could use a probe and just put your probe on there. Okay. And at that point, you are measuring basically this point here is the same, goes all the way back to this cathode here, and this point here goes to the anode here. So you are measuring across that SCR. So with this fluke lead here, you have just checked Q301, and you should see OL on your fluke meter. Doesn't matter which way you do it, if you have the black lead here, the red lead here, or the red lead here and the black lead there. It doesn't matter which way you do it. You should see OL or extremely high resistance for a good SCR, because SCRs 99% of the time fail short circuit. Okay. And if we have a blown fuse, that pretty much makes it 100% that we have an SCR that is shorted. So that's how we checked Q301. So now all we do is move our probe. We had it attached here. We now move it here. We've left our alligator lead on 338. We haven't moved that one. We've just taken our other probe, and now we've moved it here. So now we are testing Q302. Once again, you should see OL or very high resistance. And then we move our lead down to wire 360, which is connected to here, which is this one. So we've now tested the top 3 SCRs very quickly and very easily by leaving this lead here at all times, and then just going this one, or this one. So we have tested all 3, okay? And now what we need to do is we need to test these 3 down the bottom. So now we do have to move this alligator lead, and we move it down to this point here, which is wire 337, which is the negative DC bus. Okay. And then we do the same thing again. We go on this cable here, and if you follow it down, that goes to the cathode of this one, and then this is on the anode. So we have now tested that SCR. We're looking for OL or high resistance. Then we've moved our probe to this point here, which is the cathode of that SCR. We're on the anode here, and we've tested that SCR. And then we move it lastly to the last cable 360, and we test that SCR. So in a very short amount of time, we have tested all 6 SCRs. And you should see OL. And the reason we should see OL is because an SCR is like a diode. But it's a diode that needs permission to become a diode, okay? So when you don't send a gate signal to an SCR, it is an open in both directions. That way or that way, it is an open, okay? And if we have the power off, that is what we're checking. We're checking that we have an open in both directions. It's only when we send a signal to the gate lead that we then say, okay, we are giving you permission to become a diode. And therefore, when you send a signal to an SCR, it's then saying, okay, you are now a diode. And it still has to say, okay, the anode has to be more positive than the cathode, and current has to flow in that direction only. So that is what an SCR does. So keep that in mind. When you are not sending a gate signal to the SCR and you have all power turned off, it is basically just an open circuit. You should not have any power, any resistance to show you that there is a path for current. Hopefully that makes sense. And just a little bit more about how SCRs work. So here's an AC input, okay? And we're putting a sine wave into this circuit. Here is the lamp, and then here is the SCR, okay? If we do not send a gate signal to the SCR at any time, then the lamp will never, ever light, okay? Never. The lamp is only going to light when we send a gate signal to the SCR. And basically what this circuit here is a very basic dimmer circuit. We can control the amount of current or voltage that goes to this lamp. So you can see here, the blue waveform here is our sine wave going in from this circuit here. Because we only have one SCR, it's only a half wave that's getting through. This portion here does not get through to the output. And what we're saying is, if this is the gate signal, and if we tell the SCR to turn on right at the start of the sine wave, then it says, okay, I'm a diode, so I'm going to allow the whole of the sine wave through. Once again, we send another gate signal at this point here, and it turns on. And remember I said that with an SCR, we cannot remove the gate signal to turn it off. And you can see the gate signal is only on at this point here. It's not on here, 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 or here. And it doesn't turn off. The only time it turns off is when it goes past the zero crossing point. When the voltage across the anode and cathode, there is no potential, 0 and 0. So there's 0 there and there's 0 there. That is when the SCR turns off, and then it waits to be turned back on again. So basically at this point here, the lamp is going to light at its full brightness. Now, what we're doing here is we are switching it on just before the halfway point of the sine wave. So it's only this portion of the sine wave that's getting through. Okay. Once again, once it gets to the zero crossing point, the SCR switches itself off. So we can only control when the SCR turns on. Okay. That is the only thing that we can control. So in this circumstance, the lamp will be round about half bright. Half bright. Okay. And then lastly, we're triggering the SCR very late on in the sine wave, and we're only letting a very small portion of the sine wave through. And once again, we're only telling the SCR when to switch on. We cannot tell it when to switch off. It only switches off at this zero crossing point every single time. Okay. So therefore, the lamp is going to be dim at this point. So hopefully that explains a little bit more about how an SCR works. So another test that you can do if you suspect that there's a problem with the SCRs is attach an oscilloscope to the output of the rectifier bridge. Now, you're not going to do this if one of these fuses have blown. So if one of these fuses have blown, that tells you there's probably a shorted SCR or a short somewhere in this part of the circuit. If the output of the system, let's say the output of the system is not giving you full DC or any DC, and you've checked the AC input breaker, you've checked the transformer. So now the next part is to check the fuses, make sure that the fuses are good. And if the fuses are good, then it may well be that the firing signals for the SCRs are not working. Okay. So what we can do is we can attach an oscilloscope to the DC. It has to be before this choke here. Okay. If you attach your oscilloscope at this point here and this point here, because of this capacitor, you would just get flat DC. Okay. But if you attach your oscilloscope before this choke, you are monitoring the switching of these SCRs. And what you should see is for a 6 SCR bridge, which is classed as a fully controlled rectifier, that is 6 pulses at 60 hertz. So 6 times 60 equals 360. So the frequency of your output waveform from your rectifier bridge should be 360 hertz. And this oscilloscope is showing you that is correct. Okay. And you can see it's very uniform. All of the pulses look pretty much identical. Okay. You can see that this is where the SCR turns on, and then it goes over here, and then the zero crossing point is there, and then it keeps on happening over and over and over again. Okay. If there is a faulty SCR that's not getting a gate signal, then it's probably going to look more like this. You can see that's not uniform. We should see more pulses here and here, but there are pulses missing. And you can see that the frequency is no longer 360 hertz. So if we saw this waveform here on the output of the rectifier bridge, we know there is a problem with one of the SCRs firing. And it could well be that the control board is not sending the correct signal, or that there is an issue on the wiring between the gate signal and the SCR itself. Okay, so if you see a waveform, it could be this, or it could be that there is no pulses. Then you know that it's something to do with either the firing from the control board or the connections of the wires at the SCR themselves. Okay. Now with the control board, our default reaction is if the SCRs aren't turning on, then it must be something to do with the control board. And in some cases that is correct. But we always want to try and check that the control board is doing what it's doing. And a control board is relatively simple, although it can look complicated because of all the components that are on it. But basically, it needs an input, a sync reference to know at what part of the AC waveform the circuit is in. Excuse me. It needs a feedback circuit, so it knows what the output is. And then it's got its output, its firing signals to the signal. And then you have to have a set point. So really, there's only 4 parts of the control board that we need to look at. Okay. Now, a very simple thing you can do, and for AMETEK systems, if the power is on to the system, you can do a quick check for the gate signals using a fluke, and put your fluke on volts DC, and it should be around about 1.5 volts. So basically, if you went between this point here and this point here, this point here and this point here, this point here and this point here, and then this point here and this point here, this point here and this point here, and then this point here and this point here. Now, it should be around about 1.5 volts. If it's 1 volt, not terrible. If it's 2 volts, not terrible. The most important thing is that they should all be relatively similar. Okay? So if you saw one that had 1 volt, 1 volt, 1 volt, 1 volt, 0 volt, 1 volt, if you see a 0 volt, then there is an issue with that firing signal going to this SCR. Now, don't think at this point here that that's a control board issue. It could well be that something within the SCR is dragging that power supply that's telling it to fire down, or it could even be this surge suppressor that's dragging it down. Don't automatically, if you see a 0 there, say, okay, I have to replace the control board, because it could be something external. So in that circumstance, what you would do is you would either lift the lead at the board or lift the lead at the SCR and check again. And if it goes from 0 to maybe 1.5 volts, then you know that the board is sending a signal and something in the SCR or the wiring is bad. Hopefully that makes sense. So obviously, if you think you've got a firing issue, check the wires between the board and the SCRs. Okay, you need to check. You could even do a continuity check on your fluke. You can put it on resistance and go from this point here and find SCR 301, find a gate lead, and then do a resistance check between these 2 points and make sure that it is as close to 0 as possible. Okay, there may be a break in the cable. There may be something wrong with the cable itself. And then you need to check the connection at the SCR itself. So this is the most common SCR configuration that we're using these days. Okay. Now, once again, I don't know how this pack is laid out, but it's usually something like, oh, my drawing is terrible. There's two SCRs back to back. So this middle one will be the cathode for both. This will be the anode for this SCR, and this will be the anode for that SCR. You have to look at the side of the device that you have to get the configuration. Okay, but the most important part that I'm trying to get at is these terminals here. So that's the gate cathode. Let's just say that's the gate cathode. Let me draw this properly again. My pen is not drawing very well. So this is the gate cathode for this SCR. So let's say this is the gate that goes down there, and then this goes to that point there. Okay. And from our control board, we use these push-on connectors here to push on here. Now, when people replace these SCRs, sometimes they're in a difficult position, and you think that you are getting the push-on connector onto the spade connector here itself. But sometimes you can actually jam it in between this plastic piece here and this side here. And the connection should be good enough, but it's not correct and could give you a high resistance connection. So you have to make sure that this is actually inserted on the spade connector itself. And what you can also find is if somebody was rough when they replaced the SCRs, or somebody has been messing about with the cables connected to these terminals here, these terminals go down inside the SCR, and there is a very thin cable that goes down to the wafer regions, the semiconductor regions in here. And if somebody has accidentally pulled that terminal off, there may be an internal disconnect between what's supposed to be the cathode lead going down to the cathode, and that's broken. If that's the case, you have to replace this whole SCR. And there's no real way to check that. But what basically, if you check the connection and it's on here, you know the control board is sending the correct signal to the SCR, and it's still not turning on, then it is probably something within the SCR itself that is causing the issue. Okay. And then also, if this is the gate and this is the cathode, you have to make sure that the gate lead from the control board is connected to the gate, and the cathode from the control board is connected to the cathode. If you get these two swapped, the SCR is not going to fire. Okay, so you have to make sure that the wiring is absolutely correct versus the drawing. So another thing on most analog systems is the control board will create its own DC power supply. Now, sometimes, especially on our new systems, we have an external power supply, and that feeds a 12-volt signal to the board. But on our older systems and our analog systems, this board here creates its own power supply. And what it does is it takes the AC from the auxiliary windings on this transformer, and it creates a power supply on here through a diode bridge. And it's basically around about a 24-volt DC power supply, which then distributes that to 15 volts to all of the op amps on this control board here. Okay. So one thing that you need to do is check that the power going to that board is okay. Now on our systems, it says here that it should be around about 42 volts. Okay. So if you go between 1 and 2, 2 and 3, and 3 and 1, depending on the design, you should see roughly 42 volts. Okay. And at the top of our power supply, we have an LED. Sorry, on the top of our control board, we have an LED. And that LED is derived from that 24 volts DC power supply that we're creating on the board. So if that LED, power on LED is on, we know, yep, okay, power supplies are working. Okay. If that LED is off, there is no way that you can get the SCRs firing on these terminals here. You must have this LED on to fire the SCRs. Okay. Also, not only does it use these terminals here to create a power supply, it's also using that as its monitoring. Because remember in that drawing where we had the sine wave, and then we had the SCR, and then we had the gate lead, and then above it we were firing the gate lead somewhere during the sine wave. So let's say it was at that point there. Well, we need to know where about in the sine wave we are at all times. So there is a sync signal, which is not to be confused with a synchronization of a UPS. A sync signal that's basically saying, okay, this control board here needs to know what portion of the sine wave we are at before we send the signal. So that's what these are also doing. And what we found sometimes is if somebody goes in and replaces a transformer, they get these connections mixed up. And instead of connecting this connection 3 down to here, they connect 3 down to this winding, and that gets the sync off. So this control board here is now not reading the correct winding for each SCR pack. So it's trying to fire the firing signals based on the sync signal that is incorrect. And then these SCRs are going to fire out of sync, and you're not going to get the correct output or any output out of the system. So really, it's only if this transformer is changed or if this control board is changed and somebody replaces this wire and puts it over there instead of to that wire there. The power supply LED will still come on because you've still got 3 phases going in. It doesn't care about that. But the sync signal for it to know when it's firing is very important. So do check. So you have to check the drawing. Does terminal 3 go down to that auxiliary winding termination there? Use a fluke on resistance and make sure it does. Now, the control board also needs feedback. It needs to know what the output of the system is. And this is where the feedback gets fed back to our control board. So it's on terminal 4 and terminal 7. Okay. And basically what it's doing is it's feeding back the complete output voltage of the system. The 0 volts goes up here through that relay and out to there. So these 2 terminals here, you should be getting around about 135 volts for a 60 cell system. That's the feedback that it's expecting. And if that goes down, then the control board says, okay, the output of our system's gone down. I need to increase the firing signal of all of these SCRs. And it turns the SCRs on earlier. And if the voltage went up, if it saw that the voltage went up to 140 volts DC, for example, it would say, okay, I need to turn the SCRs on later in their sine wave to lessen the amount of power that goes through the SCRs, and the voltage would go down. So it's a constant feedback loop that's going through there, okay? But one thing that's important to note about our system is on our analog systems, we have K304 coil relay connected in series with the 0 volts back up to this control board here. And that's basically to disconnect the control board if we have an AC power failure. So you can see here that the coil, this is the input transformer. Okay, that's the input transformer going in. Across one of the phases, K304 coil is connected. So if we have power to the system, this contact here closes and allows the 0 volts to get up to this point here. Okay. Now this relay does fail and does cause problems. And it's because it's on the 0 volt rail, you should not measure it with voltage, because if this contact is open and we've got 0 volts here, if you measure on this point here with voltage, whether it's open or closed, you're going to get 0 volts pretty much. So what you need to do is either measure the resistance of that contact, or the best way to do it is go from pin 7 to pin 10 and pin 7 to this point here to see if you have the full 135 volts. In my opinion, not a fantastic design. It does what it's supposed to do, but you do have to check this. So basically, if you have no output on the system whatsoever, it could well be that this feedback relay is open, and when we have open feedback, the system shuts down. So the easy thing that you would do is just pull K304 and see if the charger starts. If the charger starts, then you know there is something wrong with K304 and it needs to be replaced. And also, the charger needs to know what voltage you want. So on our analog systems, we use the float equalize circuit that is drawn at the top here. So on the next page, we go down a little bit to explain it. So basically, this is our control board here, and then we have an external float and equalize pot, which is usually on the outside of the charger, so you can set the float and equalize voltage. And what happens is, on the control board itself, on pin 9, we send around about 10 volts DC that goes out to this dual point here, okay? Now, if you have float selected, then K306 will be closed, and this 10 volt signal will go down into the float pot. So this is the float potentiometer here. And how you adjust this pot to have more or less resistance, and that will change the ratio of DC that goes back here on pin 10, okay? So basically, this circuit here is setting your float voltage. And what you would do is you would connect your fluke to the output of the charger, and then you would adjust the float pot so the output is exactly 135 volts for a lead acid battery, or consult with the battery manufacturer's data sheet. And then if you press the equalize button, K306 will energize. So this contact here will open, and then this contact here will close. So the same 10 volt signal is now going through this point here into the equalize pot, which then goes down here back onto the control board. So in some charger manufacturers, they have a system where if you adjust the float pot, it also adjusts the equalize ratio. But on our system, they are completely separate. You can adjust the float and the equalize, and they have no reference on each other whatsoever. Okay. I knew I would waffle too much. We're getting close to 11 o'clock and it's just about finished. Okay. And then also the system needs to know how much current is flowing through the system. So they have a current detection system, and its main reason is to protect these SCRs here. So let's say, for example, we have a 50 amp charger. So what we're probably going to do as the manufacturer is we're going to put 100 amp SCRs in here. We usually overrate our SCRs by at least double. So we would put 100 amps SCRs in here, but we still need to make sure, because this transformer is still capable of providing us quite a lot of current. So we have to have a circuit that says, okay, no matter what, we cannot exceed 100 amps through these SCRs. So what we have is a shunt circuit. This is a shunt, which turns current into a millivolt signal to this control board. And then we have a circuit on the control board that says, okay, if this is a 50 amp system, whatever the ratio of the millivolts going back to this control board is for the amps, let's say we want to have, we want 120% current limit. So it's a 50 amp charger. We're going to allow 60 amps. So we're going to set this control board to say, okay, I'm only going to allow 60 amps to throw through that shunt. And if I go above 60 amps, I'm going to start phasing back the SCRs, which will lower the voltage, which is that's just the only way we can control the output of the system is with voltage control. So we're lowering the voltage to maintain 60 amps flowing through that to protect these SCRs, because if we allowed 120 amps to flow to the load circuit, these SCRs would then see too much current and they could fail and the fuse would blow and it would be a bad day. And then the last two components are the filter circuit. So you can see here that I've got highlighted C301. That's a capacitor, okay? And it's actually a capacitor bank. It's usually more than one capacitor. And it's there. If you remember the waveform that we had out of the rectifier, so if you measured between here and here with an oscilloscope, this was the waveform that came out. Well, the capacitor charges up when we're at the peak here, and then it will discharge between these points here and these points here. And basically it fills in the gaps, and therefore the output of the system when the charger comes on will actually look like that, and it's more like DC. So that is what the capacitor is doing. So obviously if you go in and look and you see a waveform that looks like that, and we have a capacitor in the circuit, there's a good chance that the capacitor has failed open, and you need to replace the capacitors, okay? And then we have this choke here, which is part of the LC circuit. So L is inductance, C is capacitance. It's tuned for our system at 360 hertz, and basically it helps smooth that bump out even more. So an inductor resists a change in current, and a capacitor resists a change in voltage, and the two acting together smooths out the output. An inductor very rarely fails. If it does fail, it's going to fail open. If it fails open, therefore you cannot get an output on the system. So if you don't get an output on the system and you think the inductor has failed, power the system down, go on this terminal here with respect to that terminal there, on resistance on your fluke, and see if there is a connection. If there's not, then that choke has failed and you need to replace it. Woo! I'm 2 minutes over schedule. So hopefully that gives you a good idea of how to troubleshoot the very basics of an AC to DC rectifier using SCRs. Now, there are many other different designs. There's a lot of charges using IGBTs now. I'm not going into that on this presentation whatsoever. And while I go through this this last portion to say goodbye, if you have any questions, this is the time to type in your questions in the Q&A section, and I'll see if I can answer them for you. Okay. So we've got a question already. With many points of failure relating to the circuit board, is the answer almost always to just replace the whole control board? Are they generally expensive or hard to procure or replace? That's a difficult question to answer, because like I said, it's the control board really only has 4 inputs and outputs. So if you check all the inputs and outputs and you're not getting what you expect, then you can narrow it down and say that it is the control board. But what I don't want people to do is think, okay, if I order a new control board, that's going to fix everything, because that, unfortunately, that's not the case. So yes, are they expensive? Any control board from an OEM manufacturer is relatively expensive, because we've got to keep up with the R&D and everything on that. And they are generally from AMETEK SCI. You can get them very, very quickly. We can usually overnight them to you. So it's not a problem. And we don't have any supply chain issues at the moment with charger control boards. So you can easily get one. It may be easier just to say, okay, replace a charger control board, or if you keep one in stock, then you can use that as a general fix-all. But there are many other things that can go wrong with a system that you replace a control board in the system, the fault remains, and you've just wasted time putting in a control board when it's something else. So it's difficult to say whether you should just try a control board first. Because we're the OEM and because we're subject matter experts, we would recommend no, but I understand out in the field, if you have a charger that's down, it is a good thing to try first, I suppose. Okay, I don't see any more questions going in. So London has done us a favor. Basically, she's put two things in the chat bar there, okay? First of all, if you need any other assistance from us, even after the Q&A session is over, feel free to contact us via our contact form. You can go to solidstatecontrolsinc.com, contact us. She's put the link in there. Or you can email us at sci.marketing@ametek.com, or you can get on the phone and a human will answer. 1-800-635-7300 if you have any other questions. And also, London has left the link for the YouTube channel in the chat bar as well. So by tomorrow, the video will be available on our YouTube channel. And I see another question has come in. Can you also prepare the presentation about the adjustment of the charger board? I can see if I can do that for one of our future presentations on how we can do the adjustments. And London has also put in a link in the chat bar that we would really appreciate it if you can. It only takes 2 minutes. Please click on the link that she's put in for the survey. And like the question that just came in from Damjan, if you have a recommendation for what you would like our future webinars to be about, then you can click on that survey. I think it's question 5 or question 6 that asks, what would you like a future webinar to be based around? If you type that in there, I read every single survey and I will do my best to incorporate your suggestions into one of our future webinars. Okay, it seems like there are no more questions coming in. Like I said, if you do have any more questions, you can reach out and contact us. But I'll just say my goodbyes now. Once again, I really do appreciate you taking time out of your day. I know you are busy people and there are many, many things that you could be doing rather than listen to me and watch me do this presentation. So I do appreciate you turning up week after week, well, month after month actually, to watch these presentations. And I look forward to seeing you on our next webinar. So until then, please keep an eye on your emails. We'll post a week in advance what the topic of our next webinar would be. But until then, take care. And I really appreciate you taking the time today, and take care until next time. Thanks very much, everyone.